So let's talk about section 3.3, power functions and root functions. So our objectives are going to be to kind of look at the basic power and root functions and learn how to identify the basic shape of their graphs as well as solve some equations with power and root functions or equations. A power function is a function of the form y equals a times x to the power of b. Now it makes sense why I call it a power function. Now, with that being said, there is a couple of rules on what can happen here. So since this is going to be y equals some number, and then x can be, say, to the power of 1/2, we could have x be to the power of -3. Anything we really want, the only rule is that b itself cannot be 0. Now I can also put numbers in the front here, so I can put, say, 4 in the front here. I can even put, say, negative numbers in the front here or fractions. I have a lot of wiggle room. Now let's look actually why power functions are actually important. Now, say, for example, the wingspan of birds. Now, at 17 feet, the wingspan of a prehistoric bony-toothed bird may have exceeded that of any other bird that ever existed. Now, the animal weighed about 64 pounds and soared the Chilean skies 5 to 10 million years ago. Now, the wingspan of the bird can actually be estimated by a model. Now, the model is L equals 2.43 times W to the power of 0.3326. Now, L is the wingspan in feet and W is the weight in pounds. Now, this is basically what we're going to do is we're going to graph it in the context of this application. We're also going to use the function to compute the wingspan of a mute swan that's going to weigh about 40 pounds, and then we're going to use the function to approximate the weight of an albatross whose wingspan was like 11 feet and 4 inches. And then we'll also talk about, is that actual graph of that function concave up or concave down, and what does that actually mean in the sense of what we're looking at. So the first thing you hopefully noticed was the fact that there is a formula, and it also talked about what each one of those variables represented. You'll notice that I am not using x and y. I'm using L and W. W to represent the weight in pounds and L to represent the wingspan in feet. So basically, we can use this model for the wingspan of any bird and just kind of get this idea of how it came about. This is not to say anything about the birds that we are already studying, this prehistoric bony-toothed bird. What it is like they've taken and done all the math, and somebody's already given you the formula and said, hey, this is the formula. And then you get to kind of play with that and just say, hey, okay, if I know this about the bird, what would their estimated wingspan be if I know the weight? Or if I don't know the weight but I know the wingspan, what should I expect their weight to be? Is it perfect? No, it is an estimation. So let's talk about the graph of this function, and let's make sure that we understand kind of the idea where everything is. Now remember, L represented the wingspan, and we also said that W represented weight. Well, first of all, a bird is not going to weigh negative. Like, there's just, no, not going to happen. We also know that the wingspan is not going to have a negative wingspan. So we are going to only have to be able to graph it in the first quadrant. So when I actually plug this into the function and say I plug it in my calculator, I should only look at quadrant 1. Now this may mean that you need to adjust your viewing window to what you may happen to show the graph. Now as you guys can see here, the y value is going to basically equal L, which is our wingspan, and W will be the weight, and we know that birds can be anywhere from really, really small or super, super large. The larger the bird, the possibility of the larger the wingspan is. So with the weight being heavier, sometimes we might get some very heavy birds, and you might have to go past 10. You may need to kind of scroll out further, and you can kind of see the basic shape of this graph. Now, as I noticed with the shape of this graph, it's kind of got this like curve here. And what I do notice about this is basically what we call our power function. This power function, again, was to the power of point, and then it has 0 point and then a number. Because that number was less than 1, this is kind of why we have this shape to it. Okay, so let's use that formula, and we're going to use the function to compute the wingspan of a mute swan that weighs 40 pounds. In order for this to work, basically we're going to take that function and we're going to take W, okay? So we're going to take the W right here because that's what we need to plug in. Now, before I make any plug-in, I always want to remind myself that W was in pounds, and this is also in pounds. If this is not in pounds fully, we cannot use the model. So I'm going to plug in 40 right where I said it needed to go. Now, this, like I said, this is 40 to the power, so that 2.43 is being multiplied to 40 to the power. Remind yourself, order of operations comes first, and so the exponent will come before you do the multiplication. And guys, this is one that you're not going to know by hand, so go ahead and use a calculator to help you compute it. So you're going to put 2.43 times 40 to the power of 0.3326, and you're going to get L is approximately equal to 8.288. Now, what that means is that the wingspan of a mute swan that is approximately 40 pounds in weight should have a wingspan of 8.3 feet. Okay? So this is kind of where that is very, very helpful for us, that we can kind of see what it should be approximately. Now, is it perfect? Absolutely not. But it kind of gets the idea there. For those of y'all that are trying to use calculators on your phone, I do not recommend using the calculator on your phone, like the most basic calculator. And the reason being is because there's a lot of hard times of it trying to enter in correctly. So because of the issue, like I said, with your cell phones and you're trying to use them as calculators, well, one, a lot of times you're not allowed to use a cell phone when you're taking an exam. So whether that's in person or even on a computerized exam, you should not be using the cell phone calculator. So for that purpose, make sure that you're using whatever calculator you're going to be allowed to use on the exam. So let's now use the function to approximate the weight of the albatross, whose wingspan is 11 feet 4 inches. Now, in order to find this answer, we currently do not have the algebraic method yet. We'll get to that in another slide or two. But to help us solve it with what skills we have, we're going to use the graphing calculator side of it. So in y equals, we're going to put our function. So you should be typing in that y equals and then that 2.43, but we don't put w, we're going to put x to the power of that 0.3358, okay? And that's basically what you're going to put in for y equals. Now, for the other part of it, I need the 11 feet 4 inches. Now, we have a small issue with that. And the issue that we're going to come across with on this one is the fact that it says it is 11 feet 4 inches. The model specifically said it was 11 feet 4 inches has to be combined with the model into one unit. It did not say feet and inches, it said feet only. So this is going to take some of the skills that we've learned in previous classes, you know, maybe back in like elementary school or before that. So we remind ourselves, we know automatically that 12 inches is basically 1 foot. So therefore 4 inches is going to be 1/3 of a foot. Now, if you're a little unsure how I did that math really quickly, basically this is the same thing as saying 11 plus 4/12. And if you put that all in your calculator, that's going to give you that 11.33333. You can actually type it in the calculator just like this in y equals as 11 plus 4/12, and it will draw this beautiful line right here. Okay, so that would be extremely helpful. So you know that this is a line and that is that. And you won't have to worry about any rounding errors if you did this way. Otherwise, you need to make sure that when you're working on this, that you have it set to pretty much make sure that this right here is got a ton of 0.3s afterwards, so you don't have any rounding issues. Okay, so now we can use the intersection method on the graphing calculator. Now remember how to use the intersection method on the graphing calculator. Remind yourself that basically that meant that we basically said second, and then once you hit second, you're going to hit the trace button, because right above the trace button went to the calculate menu, and then it's going to ask you that series of questions. Again, down here at the bottom, it's going to ask some questions, and it's going to say first curve, second curve, and then your guess. And again, try to get it as close as possible, and the calculator will spit back out the answer at the bottom. It'll say intersection, and this is it. Okay, I do recommend that you've adjusted your window so you can see that intersection before you do the intersect method. Now, the next question was part D, is I asked you whether it was concave up or concave down, and what does that actually mean? Well, as we can see here, it does look like it kind of curves, and it curves opening in a downward motion. Okay, again, remind yourself back to chapter 3, section 1, we learned a little bit about quadratic equations, and one of the first things we learned about quadratic equations is we basically learned that if we had a happy graph or a sad graph. And in our case here, if it was happy, it was concave up, and if it was sad, it was concave down. Notice that this graph does not look like that happy smile. It's kind of a half a smile, but it doesn't look like it's a happy. It looks more like it's the half of a frown. And since it looks like it's half of a frown, that's how I know I can say, oh, well, this is basically concave down. Now, what that means and why is it so important to know that if it's concave down? This tells us that the weight of the bird actually increases. And again, here's that weight of the bird there. We can see that it is increasing. Okay. There we go. So as the weight increases, so as we go across the weight here, then we can also see that the wingspan is also increasing. So therefore the wingspan increases, but it increases, and we can see that it gets really, really high quickly, and then it starts to kind of almost level out. It doesn't fully level out there, but it's beginning to increase at a slower rate. So here it increases slower than it does here. Here it increased really, really quickly. So it kind of, as we are increasing that wingspan, the rate it changes starts to get smaller and smaller. So now that we've had an idea of power functions, we now need to talk about what we call a root function. Now, again, if you're unfamiliar with what a root function is, a lot of people think of these as like square root or cube root or fifth root or fourth root. Okay, root functions are just a very specific kind of a power function. So we talked about power functions can basically be any, again, I'm going to kind of write on the slide here so you can remind yourself that we said power functions can basically be anything where we have a times x to the power of b. And the only rule that I had on b was b itself could not be 0. Now, if b meets a very specific form, okay, so if b meets the very specific form of 1 over a number, okay, and we'll call that number an integer number, meaning positive or negative here, then that meets the definition of what we call a root function. And again, it's a power function, but a very specific kind of power function. Okay. Now, with that being said there, again, there are pretty much two different shapes to our root functions. So our first shape that we have when we look at them is this one here. And this one kind of starts at 0 and keeps going forever and ever in kind of like an increased motion. Then we have our ones that kind of go forever left and right. So the domain is basically all real numbers. So that kind of actually is a little bit different because of the root. So this is what we call our basic kind of square root function, or also known as kind of our even root. And when we look at our even root, it basically has a domain from like 0 to a positive infinity. Now, there's a reason why we don't include anything beyond the 0 into the negative realm, because that's where those complex square roots come in. Now, this one is called what we call an odd root. And again, its domain happens to be all real numbers, because basically I can take the cube root of a negative number. I cannot take the square root of a negative number. So there's a little bit difference. But notice that when we talk about square roots and cube roots, that I am also referring to them in a exponent that is a fractional exponent. Now, again, somewhere back in previous school you learned this, but a lot of people forget it. So you learned a rule back in elementary school sometime. Like I said, it's been a minute. I think you really kind of more learned them in middle school. Yeah, I want to say it was more middle school than anything else. And the rule was basically that if you had this as your kind of exponent here, and your exponent was a fraction, we said that we could basically rewrite it to where it was an nth root. And this worked every single time. And we could take that top of the fraction and say it was on the inside, or we could say it was also on the outside. So it's actually equivalent to this as well. So I could put it all the way on the outside here. Your choice. Again, not going to like say one way is right or wrong, because they're both actually technically correct on the way to write it there. So you can have x to the power of m all underneath there, or you can have x all underneath there, but both of them are going to have an nth root. And again, the reason for that beautiful nth root there happens to be because I am dividing by n, and that is what the root is. So let's look at solving power equations. Now, with solving power equations, one of the things that we notice here is that all of these problems in particular that I'm noticing have a power where x is either being raised to that power or it's inside parentheses that are being raised to these powers. This is how I know that these are power equations. Now, again, if I am looking at 1 divided by a number as the exponent, then that's specifically a special type of power equations, which we call root functions or root equations. And we'll look at those, but for right now, we're only going to look at the power equations currently. So with my power equations, let's start with a there. And as I start with a, the first thing I want to do is I want to take that power and basically the variable that is the powers being raised to. Anything that is not being inside to the power, so like that 5, it needs to move. And we do everything by opposite operations. So I'm going to divide both sides by 5. That's going to give me 108 equals x to the third. And at this point here, I want to take a cube root. Okay. Now you're probably going, well, why don't I have a plus or minus in front of it? Well, that is because if we go back to the world of just kind of numbers that we've learned, like I said, it's probably been a minute. When I take, say, -3 and square it, I get 9. And when I take +3 and square it, I get 9. However, when I take 3 and cube it, I get 27. If I take -3 and cube it, I get -27, which is different, which means that basically, and again, follow the pattern here, that if this is positive and I cubed it, this stays positive. So if this is negative and I cubed it, this stayed negative. Whereas that was not the case when I squared it. So it had basically the same answer, but there was two different input values here. So the principle of the square root property basically is only going to work when it's an even root. And so we'll look at one that has that where we'll take that into account. But for right now, basically because it's a cube root, I don't need the plus or minus in front of it. Now, let's make sure that we are simplifying down as far as we can go. And we do have a couple of rules that we want to keep in mind. Okay, one of the rules that you want to keep in mind here is that basically if you are looking at a cube root, you want to make sure that there's no perfect cube underneath a cube root. So if you have a cube root, no perfect cube number, cube factor under the cube root. Now you're probably going, oh, well, I don't know what perfect cube factors are. Well, you actually do. It's just a lot of the times we forget them as we move up into our higher levels of math. So the first one we're going to look at is 2 cubed, which would be 8. Then we have 3 cubed, which is 27. We have 4 cubed, which is 64. We have 5 cubed, which is 125. We have 6 cubed, 256. Okay, now if you're unsure how I'm doing these so quick, is I do have some of these memorized, and it's extremely helpful if you will have them memorized. Okay, oh, it's not 256, sorry, it's 216. At this point is where I start to deteriorate. I'm not very good with most of these ones. I got 7 cubed just because it's a pattern and I like that one. 6 cubed I should have known was 216, but sorry. So basically what I'm doing is I'm basically just plugging them into my calculator. And what these are, once you get to 7 cubed, you know you've gone too far because my number's only 108 here. So I took 108 and I started dividing it by 8. And when I did 108 divided by 8, it did not divide out evenly. Okay, what I mean by that is if you take a peek at my calculator here, let's see, let's show the calculator. So I've literally just taken it and divided it, and then I got 13.5 here. Okay, this is not an even division. What I mean by that is there's no decimal. If there's a decimal, you got to keep moving. So the next one was 27. So I just basically took 108 and divided by 27, and that happened to work out perfect as 27 divided by 27 times 4 is 108. Okay, so at this point here, I'm going to remind myself that 27 is 3 cubed. Okay, and pretty much I can take the cube root of any perfect cube. It will be basically what I took the cube root of, which means that it's going to be 3 cube roots of 4. Now, if you're trying to do a cube root in your calculator like this, it will not give you an exact answer, so you are going to kind of need to keep that in mind as you're working through. So let's try B here. Now, as we work on our B example, we want to start by going, wait a second, I see that negative exponent, and I don't really like negative exponents, and I don't really know how to work with them. So we're going to make it positive, and we're going to do that by using one of our exponent rules. We learned in one of our exponent rules, and again, it may have been a minute since you've seen any exponent rules, but anytime I have an exponent that is negative, I can basically relocate it wherever I need it to go into the bottom of a fraction if it's already negative in the top, and then make that exponent positive. So again, all I'm going to do is touch this part. 4 is not being raised to that -5 exponent. There's no parentheses around it, so it's just the x. So just the x moved down to the bottom of the fraction. So that's going to be 4 divided by x to the 5th equals 512. I'm going to need to make sure that that x to the 5th is out of the bottom of a fraction. So I'm going to multiply it to the other side. Okay. And so that basically means I have 512 times x to the 5th equals 4. Again, I'm solving for x to the 5th, so I'm going to divide both sides by 512. So I have 4 divided by 512, which gives me 1 over 28 when I simplify it. At this point here, I'm paying very, very close attention. I have isolated the term that my whole goal was to isolate for. Once it is isolated, I can now take the fifth root. Now, when you take the fifth root, okay, so just to kind of keep us on the right track here, it is the fifth root of that entire fraction. But a lot of times we think of it as the fifth root of the top and the fifth root of the bottom. Now, the fifth root of the top is just the fifth root of 1 is 1. We love the number 1. 1 is the perfect every cube, every square, every fifth power, fourth power, because 1 times 1 is still 1. So if you take a square root of it, it's still going to be 1. Okay. However, the fifth root of 128, we probably want to simplify that. Now, this is where, again, I don't know these off the top of my head as well, and I'm just going to have to start by simplifying down as best I can. Start always with 2 to the power of whatever the root is. So in my case here, I'm going to start with 2 to the 5th, and I'm going to take 128 divided by 2 to the 5th, which ends up being 4. So 2 to the 5th times 4, which means I can take, again, as I'm kind of watching how this works here, I can take that fifth root of just the part that has the power of 5 on it and leaves me with just that 2 outside of the root. And so we get 1 divided by 2 times the fifth root of 4. Okay, that 4, I can't do anything else with it. It's going to have to stay underneath that fifth root there. Okay. Let's try C. Now, hopefully everybody's looked at C and went, I don't know. So again, start by looking, where's the exponent and where is X? Now, currently X is inside a set of parentheses trapped with the exponent on the outside of the parentheses, which means what we want to do first is take anything that is not inside those parentheses and move it. So I'm going to start by dividing by 4. So what that has done is that has isolated the parentheses with the power of 4. So as long as the parentheses with the power of 4 is isolated, now I can employ my root. Now this one's going to be a fourth root. Okay, now we have a small issue. So I'm taking the fourth root, but again, remind yourself, again, we talked about this, and this is like I said, because this is a fourth root, okay? So because it is even, then you are going to put a plus or minus in front of it, okay? So you have to, it's very important to make sure that you put that plus or minus there. Now, I happen to be able to take the fourth root of 625 very easily to be 5, and so it's plus or minus 5. So that means we have 2x minus 3 equals plus or minus 5. And I can separate that out, and I can say, well, that means I get 2x minus 3 equals 5, or 2x minus 3 equals a negative 5. And then I solve it out by adding 3 on both sides on both of those, and then dividing both sides by 2, and I get x equals 4 or x equals negative 1. Now, again, previously, I'm going to point this out, and again, I know a lot of people forget it. This one and this one, 3 and 5 are odd numbers. So this does not happen for these two. That is why they never got a plus or minus. And again, this goes back to the earlier slide that I showed that had the domains, and that's why, because the odd ones have a domain of all real numbers, you're good to go. It's only the ones that are even that we have to put that plus or minus there to kind of help us out. Okay, so let's talk about plugging into the calculator, because I know some of y'all are like, how the heck did she take the fourth root of something? Well, you can actually take roots better than just a square root in your calculator. So there is a way to put in other roots besides a square root in the TI-84 calculator. So to find the fifth root of, say, 16,807, what you're going to do is you're going to start by hitting the button that says math. Now, again, that's going to be on the calculator on this side here, and it spells the word math. It is basically the third one down there. You're going to hit it, okay? And when you hit that, that's going to show you this beautiful math menu. It looks something like this. Now, with that math menu, I want you to scroll down and notice that as you scroll down on number 5 there, it says X root. Now, that's the one I want. Okay, so I'm going to hit number 5 and then, you can have it selected and then just hit enter, or you can type the number 5. Either one will work. Okay, then you're going to input the root and number under the root and then hit enter to evaluate. So it should look something like this. And then once you've evaluated it, you just get the number. So my answer here is 7. And we've done this again previously in other slides. So I've done 4th roots this way very, very quickly. And if you need to, go back and try those again. But again, start to kind of get familiar with your calculator and look at that beautiful math menu. We like that math menu quite a bit. And there's a lot there that we can do. Pretty much 1 through 5 are the ones that we spend the most time learning an awful lot about. There is some other things there, but we don't really mess with them too much. They're just not extremely helpful sometimes. But the 5th root, being able to put in any root I need is going to be extremely helpful.